yesterday. So Wednesday, this is going to be all technical sessions, all methodology, very interesting. We're going to go into a lot of depth. The ground rules are similar to what we did yesterday. We're going to go on the talks, essentially trying to spend under 20 minutes, ideally more like 15. Go to the talks, bring the speakers to the front, then do a Q&A session for 20 minutes. So we're going to have, I was going to suggest that if you guys want to come a little bit closer, we have a little bit smaller group today, so it's a bit more intimate. And I think it's better for the speakers as well, especially in the QA session. Ideally, we will be kind of talking close to each other, so we don't have to walk around with the microphones later. And I want to introduce here Brian. Brian is going to help us enforce the time limits. He runs our ortho rectification team at Planet. Welcome.
Hello, everyone. So basically, I'm just going to be the timer. So if you're giving a talk, what I'll do is time you for 15 minutes, give you a heads up that you have 5 more minutes, and then we'll have a hard stop after those 5 minutes. Pretty straightforward. So, but I'll be sitting up here and I'll be yelling at you. So, thanks.
Awesome. Thanks, Brian. And I think you should keep a microphone.
I should. Go ahead.
All right, well, thank you. So I'm going to talk a little bit about Cloud 2.0. This has been a project that's been ongoing since the beginning of this year. When I joined Planet about just over a year ago, I sat down with some of the top guys, and it became really clear that this was a readily acknowledged issue for our Dove data. And so we formed this Cloud 2.0 project at the beginning of this year. It was kind of an interesting project team, and you can see a long list of people who have contributed to this project. And it was much as a lesson in building a team here within Planet, bringing people from all across the company, as well as developing the core. And so on the left here, these are the people who have been my key champions on things, and also the supplier of the talent that you see on the right. And in the brackets, you can see where I've borrowed talent from. And so it's been quite an amazing challenge to build the technology and build the team and execute work in a very interesting way here at Planet. So I just want to recognize everyone's contributions to it. It's a long list. I won't go through all the names. And it was very much a team effort here in order to address the challenges that we had here. As we know, at any given point, 60 to 70% of the world is covered by cloud. And after accounting for haze, shadow, cloud, whatever else, only really a small fraction of optical imagery that we collect every day, on the order of around 200 million square kilometers, is really usable for analytics. And so we know that every satellite operator of an optical satellite has built a cloud detection system. I've built multiple of them in my career, first at MDA, and then, not that I was part of the EarthCast project, but in building the cloud stuff, but been there and seen that happen as well there. Planet really kind of took off from kind of the Rapid Eye kind of concept of what we called it. The Rapid Eye project was the unusable data mask. And what I didn't like about that is it's not true that whatever pixels are marked as not unusable are usable. And so we tried to change the paradigm a little bit and express it in terms of a usability data map, and saying which pixels are usable and how usable are they by what kind of cloud cover or haze cover or shadow cover or snow cover they have in each pixel. And so while we call this Cloud 2.0, it's really kind of like Cloud 6.0 at Planet here, or maybe it's 7 or 8, I don't know what the exact number is. There's been multiple attempts at Planet to try and do this. It really took a lot of effort to kind of get everyone aligned with building this project and getting around that and actually executing it and getting it truly operationalized. And we are now at the point of getting this out into the wild. Before I get into things, I thought I'd take a step back and recognizing that the talks this week are all about ARD. Chris Holmes put together a really interesting blog on what he defined as analysis-ready data. And I want to kind of riff on a little bit on how he described the workflow there. There's a search and discovery part, where you download the imagery, you clip the data, you perform some atmospheric correction on it, you mask out clouds, haze, et cetera, and register all of the imagery. And so where Cloud 2.0 came along was we wanted to improve two parts of that experience. We wanted to first improve the data discovery part of it and make sure that that was really reliable. And so we've addressed that by providing very rich metadata. And then also to improve the usage step, which is where we provide the cloud pixel by pixel mapping of what their classification is. And so what you're seeing cycling through here is just an example product. You can see the Planetscope image, and you can see the different cloud masks and haze masks that were produced along the way. We started with a bit of a survey of what's out there right now, what's current state of the art. So I looked at Landsat 8, for example, and what I took away from Landsat 8, you can kind of see here. First, they've provided all these different levels of classification of what are the different pixels. And also it's worth noting that they've provided it is a 1-bit number, but it is at least a confidence measure. It says we are or are not confident that in that decision. Their algorithm is based on CF mask. It's a masking algorithm, and it's driven by decision trees. Those are not real decision trees for CF mask, but I just throw them out there for some graphics. And one of the things that I also took away from it, we expect there to be better performance given that they've got more bands than, say, compared to Planetscope. And I've got a couple of links to some of the papers that are in there. The cloud shadow was actually derived by using geometry. So they take the cloud mask and use sun illumination sensor geometry to figure out where the cloud shadow is as well. One of the things worth noting, though, is it doesn't have any kind of priors going into it. And so it does suffer in places where there's bright areas over urban environment, over salt flats, over deserts, and everything else. So there's some variability in its performance. I looked at Sentinel-2, and actually I was kind of, dare I say, disgusted with the quality of it. And I think there's been a few people speaking yesterday about some of the suspect metrics in there. What I'm showing here, and this is not an extreme example, but you'll see here what's cycling through there is the opaque mask and the cirrus cloud mask. And there's large swaths of it that are not even masked at all. It's identified as clear in their product. A couple other takeaways I had here was we need obviously more than just the opaque clouds and cirrus clouds mapped out. They express it in the form of polygons, which is very difficult to use. I think most people in this room would prefer some kind of a raster or a mask kind of thing. So it's very difficult to go from polygons to masks. But again, with additional bands, I expected its performance to be much better than it is. So I was a little bit disappointed. I did a little bit more surveying and came across a bit of a research project, I think, where they're using machine learning now to get to a better level of masking, and they've also increased the number of classes, as you can see here. So they got cloud, cirrus, land, water, snow, and shadow out of that. And so I think that's a huge improvement. I'd love to see that operationalized and become part of their routine processing operation. I searched a little bit wider in terms of what else sort of technology out there, and I came across a couple of patents, one from Climate Corp. You can read what the description there. I don't really have any nice graphics for it, and I'm not going to talk about it. The one thing that I did take away from this, and I've done this in the past, is again, using morphological operators as a way of mopping up and cleaning up some of the false positives and false negatives. Digital Globe also has a patent in cloud mapping, and it's got, actually, sorry, it's a 6-stage algorithm, and it's a form of segmentation and edge growing, and again, they do have some cleanup operations, morphological operators and whatnot at the end to kind of mop up and deal with sort of some of the false positives, false negatives that you get out of it. So what is Planet doing? We started with a bit of an architecture, and you can see it kind of outlined on the right. It's really a kind of a 5-step process here. We go through a very rigorous rate of transfer model, and we're also feeding in what you can see on the right there is a lot of prior data. We're trying to make sure that we're leveraging every bit of data that we can lay our hands onto. So we're taking in reference imagery that our mosaics team have put together for us. We've got snow data, we've got other data coming into it, and land cover data and everything else. So we're trying to throw everything in the kitchen sink at the problem. And then we go through a thresholding step. Thresholding is constructed, we use XGBoost for the thresholding, and XGBoost is a decision tree machine learning technique. And then we always recognize that thresholding doesn't get you 100% of the way. There are a lot of confusers out there, and we'll talk a little bit more about that later on. And so we have a second stage of machine learning using TensorFlow, CNN using TensorFlow to help deal with some of those confusers and try to make use of kind of the two-dimensional kind of information in the imagery to improve our performance. And then the final step is really about the metadata and map data, packaging it all up and getting it ready and delivering it to where it needs to get to. Core to this is, we call it the manifest. The manifest is this massive multi-layer image stack of different pieces of information. And I kind of think of this as kind of the first stage of almost like a CNN. We're doing a lot of band math here to get to certain indices and metrics that we know relate well to different kinds of covers. So we've got HOT, we've got haze, we've got lightness, we've got grayness, we've got shadow metrics, and we've got some other stuff coming into it. And so the point being there is we're throwing everything in the kitchen sink at it that we can, and we're going to let the machine learning try and figure out what's what and how to build that decision tree. So it's a fairly deep and complex decision tree that comes out of it, but we're trying to give it as much information as possible so that it can perform well. On the machine learning training, we started with something on the order of around 1,000 curated and hand-classified truth images. And we picked a wide range of cloud cover, haze cover, scene type, time of year, all these different atmospheric conditions. So we try to kind of cover the whole gamut of it. And we had that all hand truthed. And then we had to step back a little bit and understand how good is our truth data. So we produce what we call a consistency matrix, not to be confused with a confuser matrix, pun intended. The consistency matrix is really about trying to say, is our truth data consistent? And we discovered, in fact, it was not very consistent. We had to go back and probably retruth on the order of around 150 scenes, and I have the guys now still looking at about another 50 scenes again. And part of it comes about because we had a team of people in the Berlin office doing this truthing, and one person's haze, a light haze, is another person's heavier haze, or one person's heavy haze is one person's cloud. And so we learned some interesting things there. The other thing that we discovered is the confusers that I mentioned a moment ago, is where you start to get combinations of shadow and light haze, for example. You can have shadow on the ground being cast by a nearby cloud, but then that piece of ground is also obscured by some light haze. So you get these multi-class combinations, and so we had to kind of invent, I guess I'll call it some precedents, so that we could eventually pin it down and say it's either light haze or it's shadow. We didn't want to go down the road of having multiple classes. We thought that was going to be really complex for us, at least out of the gate. So we had to make a binary decision. Is it light haze or cloud or shadow or whatever else? And so what you're seeing here is our consistency matrix. And my takeaways from this is, we're doing pretty good on clear versus clear, snow versus snow, shadows not too bad. And then it gets a little bit hazy in the light haze, heavy haze, and cloud. And I kind of look at that little bottom right-hand corner there all as one block. And then we took that and said, okay, now let's subset our data and generate what's considered a more traditional purist confusion matrix. And so this is not operating on all the data. This is operating on some subset of the data. And what I'm taking away from this here is right now our performance is we're classifying a combination of haze and cloud correctly about 74% of the time, but if I change the subset and roll the dice again, I get a different percentage. What that kind of tells me, though, is because we see that variability, it suggests we probably still have some inconsistencies in our truth data, and we probably also have some distribution biases. If you roll the dice again, maybe you get a little bit more scenes with some more haze, or some other scenes with more cloud, or more scenes with more desert. And so it's very difficult in trying to make sure that you've got a uniform balance of all the different classes. I like this graph here. What this graph here, this comes straight out of XGBoost, and what this shows is what layers in our manifest is the decision tree most informed by. And the top three ones are HOT, HOT, and HOT. So that's the Haze optimized transform, and we've got a couple of different things in there that we flow into it, and this decision tree is reacting to a lot of that. Number 4 on that was EVI. It was a way of helping inform that model and trying to say, okay, when I'm over vegetation, I make different decisions than when I'm not over vegetation, for example. So, and all the way down the list, I won't go through the whole thing. What I'm trying to show here is actually what finally comes out at the end of the day. And so on the left is all the metadata that will get exposed. It's not yet exposed, but it will get exposed. And what the takeaway from here should be is we're putting out 2 pieces of information for every land club or for every classification, both a percentage and a confidence. And my comments the other day about making sure that we inform people about the certainty that we are in things, and I've taken that to heart for a long, long time, and you can see it being replicated here. So we are publishing our confidence metrics along with our cloud cover scores. I asked the Mosaics team, this is Kelsey's team here, to do a little bit of so what? Have we really moved the needle on Cloud 2.0? And so Maurice did a couple of mosaics for me, and what you're seeing flicking back and forth is mosaics informed or not informed by Cloud 2.0. And I think you'd agree that that's a pretty substantial improvement. Their comments, and I'm just kind of going to quote Maurice on it, is significant improvement in the elimination of the problematic haze and popcorn clouds. So that was one of his big takeaways, is that, boom, this is an obvious improvement. And so that's a good sign. I've been doing some time series analysis. I'm a big fan, obviously, of the time series, as people may have gathered. And so what I did is I took a stack of something on the order of 11,500 scenes. I picked out of that 9,000 scenes that are sufficiently clear that our processing system can actually stamp mosaic together and create a 4-band image. If it's 100% cloud, our processing system just throws that away and doesn't do anything with it. If I compare Cloud 1.0, that's our existing cloud processing chain, it thinks 83% of those scenes are cloud-free. That seems a little unrealistic to me, but there you go. Cloud 2.0 says probably it's closer to 51%. And what this graph here is kind of showing is what is the difference as a function of the percentage of scene declared clearness of the image, because we're really mostly interested in clear pixels. You can see there's a big difference between how optimistic Cloud 1.0 is and how realistic Cloud 2.0 is. I did a bit of analysis here, and I took a time series. This is looking at a single field. I just picked one of a bunch of fields. I've got probably something on the order of several thousand fields. This is in Imperial, California, and I just took an arbitrary, just dropped the needle, picked one, and said, let's look at that time series. And what you can kind of see, this is kind of the graph that we saw the other day, and I was hoping I could animate this, but I didn't quite get around to that last night. I was a little bit tired. But what you can see is the odd spike in here, and what that is misclassified cloud or haze. If the spike goes up, and if you see it drop, that's a misclassified shadow. In this particular time series, and actually in a bunch of the time series that I analyzed, we ended up with about an error rate of around 1.9% in terms of misclassified cloud and haze, and just under 2% for misclassified shadows. So you can expect out of a time series right now with Cloud 2.0 that we have about a 4% error in terms of the end results. I did a quick comparison with some Landsat. These are 14 minutes apart. The clouds have moved, so I don't have a direct side-by-side comparison, but I'm pleased to say I think we're doing really well when you look at this. And then I did a comparison with Sentinel-2. Unfortunately, the orbits are quite a bit different. We were about 42 minutes apart, and the clouds have moved substantially. I was really disappointed, though. Sentinel basically came back and said, that's clear. I don't know if you would agree that Sentinel image there in that little zoom-in area is clear, but Sentinel thinks it's clear, so I was rather disappointed here. So some lessons learned. We learned a lot of lessons along the way, some conclusions, and sort of our next steps. The big lessons I came across was check your truth data for consistency and check it and check it. And I think we heard what was it, the 540 rule the other day. Another thing that we kind of ran into, it was kind of a naive, this was the person who was implementing the stuff said, okay, we're going to feed into XGBoost. You can say what the missing data is, and he set it at 0. Well, a lot of our data is after pre-whitening the data, we have it all kind of centered around 0. And so we end up actually throwing away 3/4 of our data. And so 0 is not missing data. That was kind of a lesson learned for us. I think we can say with a high amount of confidence, this is substantially better than Cloud 1.0. And we're now working to hook Cloud 2.0 into the last mile of delivery. Sometime this week, we're expecting that asset type to get released. And there's still a bit more work to get the metadata released as well. And we're kind of stuck behind a little bit of an upgrade that's on the way. We're also now actively working on SkySat. We have some demand there to get SkySat going. And so that's on its way. Thank you.
Awesome. Thanks, Keith. Perfect timing on that one. And I think the next up is Minsu will get you set up, and then we'll do the talk right after that. Great.
Thank you. Yes. Thanks.
Good morning. My name is Minsu Kim. I'm a contractor to USGS Aeros. I work with government PMs like Greg Senzas there and John Dwyer at Aeros. We knew that the Planet folks are doing a great job in a small sat, so we were thinking about comparing between OLI and Planet quite a while, but we didn't do it. But when we were informed about this meeting about a month ago, I thought it's about time, so we scrambled this effort, and here's the result. Let me go quickly because I prepared a lot of slides. So we look at the USGS Aeros site first. Planet 3-meter high resolution pixel here, 1,000 by 1,000 pixel. That goes to 100 by 130 meter OLI pixel. So we'll also compare Sentinel data in the middle. Let's briefly look at the atmosphere correction in just 2 slides. So we have a TOA reflectance here. And in first approximation, we can just divide into 2 components, atmospheric contribution and surface component. So we got TOA reflectance here, and cyan color atmospheric component, and surface component, which is magenta. But our final goal is to convert it into real surface reflectance that you measure using spectroradiometer. So that's rho here. So you need two-way transmittance, scattering transmittance, and spherical albedo of atmosphere, sort of that. So you got satellite data, TOA, and this is our goal to solve. So that means the rest of the terms you need to somehow find out. And those are determined from a lookup table, radio transfer lookup table. So the parameters that determines those specific values from huge pool of lookup table is angular components like solar zenith angle, view zenith angle, relative azimuth angle, and atmospheric component. We get ozone and column water vapor from MODIS data. And AOT, you get it from image itself. We can talk about these hours and hours, but once you know it, then you can go to the lookup table and pick all those individual numbers and calculate rho. Planet, I think, does the same thing. That's what the GeoTIFF info structure tells me. They use 6S lookup table with these aerosol models, and AOT, ozone water vapor value that you use is well reported here. So I think the approach is pretty similar. The scene selection, the most important factor is the ARNet site. I want to have that ARNet site because I want to have ground truth reference of AOT and column or vapor. So first you need to make sure it's cloud-free data from Earth Explorer, USGS, and make sure that the date, you got the data and at the time of the scene. So I was able to get the Planetscope data only several minutes apart for each and every scene. And Sentinel data on a day ago. So eventually I get OLI data, ARD, Planet, and Sentinel. So using this data set ready, I just run with the software. First step will be just let's assume that georeferencing what they report is just accurate. So when you do it, I mean, people already talked about it many times. So you just resample it, like 100 pixels goes collapsed into one OLI pixel, something like that. So this is the result. Visually it looks pretty okay, but if you plot it, you see some of this scattering. That means there is an image shift issue. So assuming there is a delta easting and delta northing, I mean, you did it already, so I'm just going quick. You resample it again. Eventually, after this effort, it turned out that 3 planet pixels to the left and 8 planet pixels to the north. That makes the best fit, which translates to 9 meter and 24 meter. Yeah, this one demonstrates the quicker way of doing optimization of that pixel shift. But I believe you guys have much better or other well-proven effective method. But this is just came about. Because it's a non-analytical function, so you cannot use derivative-based like Levenberg Marquardt or something. Oh yeah. Okay, left pixel. If you do not make any geometric shift, then you are at the center, dead center. So you'll have certain error. But if you somehow shift to a certain way, it's showing from 30 pixels to the left, 30 pixels to the right, and north and south. So it's a brute force method calculation on the left. So it turned out that if you go there, that's the dead center that makes you least amount of errors or the best correlation. I mean, conceptually it's simple. I'm not maybe explaining better. So this is after doing that image shift, you get much better comparison and histogram for each channel, and no shift with shift. Slight difference. So we just took care of this georeferencing issue. So it's done. But we still see some tilting. I mean, it's not really aligned well to one-to-one line. Yeah, it's pretty good, but I would say that this is one of the good results. Don't forget. And so strictly speaking, this mismatch will cause some kind of errors in the downstream application, for example, NDVI. So we got the georeferencing checked. So what other reasons for this mismatch? It could be spectral response issue or atmosphere correction issue or radiometric correction, stuff like that. So you got different spectral response. We discussed about the interoperability yesterday. So to do this analysis, you need to use realistic or real spectrum. You cannot do some generic effort here. So for blue channel, either you can use this continuous equation or discrete type of equation. So I use a bright soil, sand-like pixel and dark asphalt. There can be infinite number of spectrum in between of similar kind. And dark dense vegetation to like dry vegetation. Of course, the range could be different and there's a continuous variation in between, something like that. So, I mean, you can consider other type of spectra too. But simply speaking, if you use this brightest one, Planet reports 5% more, dark dense vegetation 20% more because of this extra sensitive area in the spectrum. Well, dark dense vegetation, there's a big bulge here where the blue OLI doesn't have. That's why you get this extra. Even though you have identical target, simply because of having different spectral response, you have these differences. So this has to be corrected. So if you just blindly plot it, you will see some kind of this tilt. So in order to correct it, you need to correct lesser to the higher value and more to the DDV. But you got asphalt. It requires only 2% of correction, while this requires 20% of correction. So it's a really messy thing. Ideally, you can do it, but you can do for all other channels. So the brief conclusion here is spectral response function issue. The correction factor has to be different for varying reflectances and different classes and different bands. So ideally, you need to perform extensive modeling study that I kind of briefly demonstrated in the slide. And for each and every scene, you need to classify, and then apply varying degree of correction based on this 1 and 2. It should be fun, but very difficult, if not impossible. So currently, I leave it as it is, uncorrected. But we understand that this definitely adds extra uncertainty in SR comparison. If you want, you can do it. So AeroSec is a software that USGS Aeros developed atmospheric correction. So it looks like quite fancy software. Actually, it is. But we use this software for this analysis. So quickly speaking, I don't have much time. So just brief idea of atmospheric correction. For this non-vegetated wet dark soil pixel, TOAL is fixed. And if you apply a different amount of AOT, what you will get is, if you overestimate the AOT, you will underestimate surface refractance, vice versa. And Planet used 0.014 AOT and only got 0.018. These are actually extremely low number. Anything lower than 0.05 is just clear atmosphere. Majority is Rayleigh. There's not much of a contribution from AOT. So as you can see, virtually there's no difference, vegetation and bare soil. But AeroNet says it was 0.035. So what's the difference? Not much. So atmospheric correction error in this not quite satisfiable comparison of SR is not an issue. That's the point here. Let me skip this. So how about then, we're not very satisfied at the surface reflectance level. Then let's dig deeper to one level deeper. So let's look at TOA radiance and reflectances. TOA reflectance to surface reflectance convergence, of course, atmospheric correction. Overall, I think it's pretty good. This blue channel got the largest amount of reduction from here to here, and green the next, red not much, near infrared almost none. So the overall pattern looks okay to me. So simply it's transferred. I mean, the quality of atmospheric correction in this effort was not too bad. That's my conclusion. But one level down, radiance, that's the problem. That's the problem. Radiance has to be almost identical. Regardless of the sensor, regardless of the altitude, has to be identical. But we have some differences here. Radiance invariance law, what it says is we got the ground radiance, upward radiance, we got atmosphere. But atmosphere, as you know, it's only like 10 kilometer or at most 20 kilometer. So sensors way above looking down. So radiance invariance law says regardless of the altitude, aperture, and IFOV, they have to be identical. But it seems like we're not seeing that. So let's take a look at OLI versus Sentinel MSI. In this case, we needed 1 pixel to the left and 1 sentinel pixel to the left, MSI, and 2 pixels to the left. So it compares very well. It's good news. Planet and MSI matches georeferencing very well. So that means Landsat needs to correct by 10 meter, 20 meter, like that. After shift, this is pretty good. As you can see, RGB band dead on between OLI and Sentinel. Well, it's expected that they are good state-of-the-art, top-notch sensors, top-notch optics and electronics and everything. Let's pass this. So let's look at several examples. Sophos is here. Let's look at Seoul. And as you can see, surface reflectance is way above in this case. I mean, this is one of the worst results. So we sample the image, OLI versus Planet, it looks extremely bright. And TOAL, yes, that's a problem. And eventually, this was the main issue. I think it's a sensor specific. Remember that we are looking at out of millions and millions of scenes, I'm looking at just one scene, so this cannot tell the whole story. Comparing to OLI to Sentinel looks pretty good, as opposed to this. And let's briefly look at Toulouse, France. Not too bad here, but TOA radiance, I don't like it. Landsat to Sentinel, pretty good. RGB, some differences in near infrared. Beni Zombo, Nigeria, it's high reflectance, I mean, almost desert area, so it's pretty good. So I feel like Planet system has some issue with low signal. I mean, it's not, it can be a definite conclusion, but it looks like that to me. So let's compare all, by combining all those. TOA radiance, the most fundamental level of optical power. Here, bright desert signal to Seoul, I think, and so forth, Toulouse, France. You may see it's not too bad, but actually it's not good. TOA reflectance is simply transferred from radiance, and surface reflectance, yeah, we see some of those issues. Now, comparing to Landsat and Sentinel. Sentinel, kind of dead on in wide area. So this is kind of conclusion. TOA radiance, it is related to pre-launch radiometric calibration and afterward onboard constant monitoring and correction afterward, and sensor-specific issues, all those things are involved here. I think the problem is right there, because the conversion from radiance to reflectance is just straightforward. There's nothing new here. Earth-sun distance, solar zenith angle, solar flux, they're all important individually, but they are precisely known. There's no additional uncertainty transferred here. Looks like the uncertainty is kind of, I mean, error is enhanced here from here to there, but that's caused by this issue, not by conversion process. TOA reflectance to surface reflectance, which is atmosphere correction, I would say it's not bad. It's not bad. I mean, you may see totally different way, but in my trained eyes, it's pretty good. So I should say it's not really easy to screw up AC, right? So unless you're doing extremely bad, it should be pretty okay. Now, Sentinel comparison. Of course, they are expensive sensors, well maintained, so pretty good. But yeah, again, I didn't on purpose choose those scenes. I didn't have much time, so I just randomly picked. Somehow, just first 4 I got was this. I spent most of the time producing this methodology and software. So from now on, I can do it a lot fast, many more data. Yeah, probably I'll present more in JC. So yeah, that's a kind of conclusion. I wouldn't say more. I think it's more of a radiometric management issue. Thank you.
Okay. Well, it's not on. Okay. Thank you, guys. I guess we'll go ahead and do the panel discussion now. And let them get settled up there. And if anybody has questions, I can come to you. I didn't see the mic stand, so, and I need to stretch my legs anyhow. So if you have a question, just raise your hand and I'll come to you.
Okay. Is that working? Yeah.
Are you on?
I think so.
Yep, right here.
For the Planet Cloud 2.0,
Yes.
how do you get your training data and how much of it did you collect to be able to produce these results on machine learning?
So we had something on the order of 1,000 scenes, and we had a team in the Berlin office using a tool that we'd built, literally going in there and painting and masking out, here's the clouds, here's the haze, here's the clear, et cetera, et cetera.
Did you choose the scenes at random, or was it there a method to choosing which scenes you trained on?
we tried to make sure that we hit as many different classes of land cover and cloud, haze, shadow, and just to make it as diverse as possible so that we could try and balance out the different classes and hopefully not have too much bias one way or the other.
Would you be interested in sharing this as a SpaceNet exercise? Or, I mean, is there a possibility to get this training data?
I think we could explore that. I wouldn't mind putting that out there. I can't speak on behalf of everyone else at Planet to say yes or no, but I wouldn't mind exploring that.
Okay, thank you.
Okay, logistically, I guess we're supposed to do this over here, or otherwise I'll be going in front of the camera over and over. So I guess we're going to keep the mic over here, and we can line up on this side. So I saw somebody had their hand up. Sorry. We'll get it worked out by the third or fourth session.
Do we have another microphone?
No, we're taping this, and if we start going around here, people go in front of the camera.
Got it.
So we're trying to create a good video record.
Long walk for a quick question. So Keith, the examples you showed errors of commission. Where did you do the same? Go through and look for errors of omission as well. Where you were overly conservative in the cloud estimate, as opposed to, because when you looked at the mosaicing, you looked to show here's where when you ran Cloud 2.0, no clouds. Well, how do you know that you weren't overly aggressive in filtering out clouds? Did you check that side of it?
I think the confusion matrix that I showed actually hits both sides of it. You're on one side or the other side of the diagonal, so you can see that kind of the performance. I haven't looked specifically at that question. I think most people would agree when you have a surplus of data, you'd rather err on the side of being pessimistic and taking the best of the best, and not so worried so much about the errors of commission. If I throw a few pixels out, like if I'm doing a time series and I have like a year's worth of data and I have like close to 250 samples, do I worry if I'm missing one particular sample? Probably not so much, but we are looking at one particular thing that we have a morphological operator that we use to try and mop up, like everyone else does, to try and mop up kind of the false positives and the false negatives. I think there's a little bit of pessimism in our morphological operator right now, and I think if there's anything, that's the place where we're starting to see some of the errors of commission.
This might be more of a comment and thought for the whole group, but has anyone thought about replacing the atmospheric correction models with a machine learning model?
I think so. If you can, let me say, overall, you're taking off more to the blue band, shorter wavelength, and less to the longer wavelength. But somehow machine learning can have some category of atmospheric conditions, some better way. I'm more trained into a scientist, so I don't have that good feel for it, but you guys can come up with a good, discrete classes of different conditions based on the simple several bands information. So you can maybe make a quick table or something. It may not be that precise, but if you look at how 6SV lookup table referencing is working, it's extremely time consuming. So original form of the Search algorithm, that for example, if it took 15 minutes, later I modified it into just taking less than 1 minute, because there was all about just referencing to the table and come up the numbers and applying it. And you do it sample by sample and roll to the for loop, 8,000 by 8,000 pixels. It's extremely waste of time. But if you make some good assumption, you can do it extremely faster, making it into simple polynomial model. So yeah, in that sense, I think that you can do it. But it'll take a lot of research effort to come up with that idea.
I think it's possible. Machine learning is a great way of inverting an invertible equation, and we base all of the atmospheric correction on forward radiative transfer models. And so machine learning is a way of inverting something which doesn't have an analytic inversion of it. So I think I would agree with Minsu. I think you can do that. Your mileage may vary, and I'm not sure about the confidence number that I would put on it at the end of the day.
Just a quick question on the cloud detection stuff. I liked your variable importance measures you did in terms of what variables are contributing more to the model versus others. Did you use that to down select any of your variables, or did you look at how correlated a lot of your variables were?
We have that on our kind of our radar in terms of thinking about what we want to do. We did think about maybe dropping some of those lower classes, and I haven't looked really at the correlation. Are we, if I was to randomly select our inputs, would I see that importance ranking change, for example? Because that's really a way of kind of jittering it and saying which one is it really truly sensitive to, and what ones are meaningful and what ones are not. We haven't done that piece of work. Right now it's just been a race to get it commissioned and operational and getting it out there, and then we kind of step back, draw a breath, relax for a second, and then try and figure out, okay, what we need to do to make it a little bit better. But it is something that we gave some thought to. There's two ways we can play that. We can play that with a weighting, or we can just drop it out, which is like setting the weight to 0, essentially.
Given that you're including them all, do you have any concerns, or have you looked into if you're overfitting a little bit?
That's been a long discussion between myself and the persons who've been leading one part of the machine learning. I don't know the answer to that just yet. 1,000 data sets is really not a lot. We were giving some ponderance to how can we synthesize some of our training data using GANs or something else. And I felt that was going to turn into yet another research project to prove that the GANs results were meaningful and that we weren't just fitting to that as well. So it's a bit of a struggle. Getting good truth data is really, really hard. Validating and making sure that truth data is consistent is really, really hard. And then as you reach into that data, and I commented on it about our consistency matrix versus our confusion matrix. All right, I found it more informative to look at the consistency matrix and say how good is our data set versus the confusion matrix, which is kind of you take a subset and then you get random results in it, and I'm not really sure what that tells us at the end of the day, other than we have maybe some inconsistencies or selection bias.
A couple of pro tips in terms of cloud screening algorithms. It's always worth doing a clear observation count across a deep temporal stack, because if there are any observation biases in there or any issues in the cloud screening algorithm, they'll pop out like that. We're running FMask on both Landsat and Sentinel-2. FMask for Sentinel-2 doesn't work particularly well, and it has a tendency to knock off bright white roofs as clouds consistently. I think a nice little morphological chunk. So this is a kind of a call out to all providers of analysis-free data and cloud screening algorithms. Do a temporal summary of the cloud screening behaviours, and make that available to end users so that they can understand if there are if you are consistently hitting a particular target and mislabeling it as cloud, then you have an informed user base.
Yeah, we do have a bit of an issue right now with our reference imagery, that where we have really bright soil and our reference imagery doesn't necessarily capture that. Just by the way that we're processing our reference imagery right now and preparing that reference imagery, we do have a couple examples where I've seen really, really dry, bright soil, and we do see that kind of coming through into our masks. And so we're working right now with Kelsey's team to build some better reference imagery. What I think is really critical here, and trying to solve like the Landsat CF mask problems, is they don't have that reference image. They don't have that prior going into it, and so that's why you get all of those issues. But there's issues now when you bring a reference image in it as well. And so we're trying to find that right sweet spot between the two.
Yeah, I guess my point is there isn't a perfect cloud screening algorithm, and doing a clear observation count is a very quick and elegant way of figuring out exactly where your errors of commission, systematic errors of commission occur, and that's a very useful piece of information for consumers of any of our data sets.
Okay, thank you.
So that's a question for Mr. Kim.
Kim, yeah.
Yeah. With this radiance differences, could it be that when you neglected the difference between the spectral signatures of planet satellites and Landsat, you actually, that's where the difference comes from, not from planet being not calibrated, but planet getting more radiance out of the atmosphere because it has wider spectral bands?
Yeah, that's what I was discussing about the spectral response function issue.
So, I mean,
it's an added signal. So yeah, based on that, you can see channel by channel, the tilting angle could be different. I saw it. I didn't go through channel by channel, but on the blue channel, you saw higher in the planet in the smaller reflectance area, but in other channel, it has kind of a little different angles, something like that. Yeah, as I said, you may do it, but
yeah.
I didn't do it. But I don't think that really fixed the problem, because I see kind of random direction from different sites.
Okay,
But
thank you.
yeah, it's a homework.
One of the questions I guess I have coming into this week is whether we would want to try and settle on surface reflectance as sort of the ARD product, or maybe one of the main profiles. So what I hear from your presentation is that you feel that the transfer from top of atmosphere radiance to surface reflectance is well understood and well behaved between, at least those three examples that you gave. I'm wondering how close that brings us to being comfortable with saying, okay, we think everybody could convert to surface reflectance without significantly damaging or impacting the data, or what other, next steps we would want to go through for that. I'm particularly concerned that maybe we're all just using the same inputs for aerosols and stuff like that, and that sure we're all getting the same transformation, but that's not. We might still be damaging the data in ways that weren't totally represented in your analysis.
Yeah. First, the best effort you put for atmosphere correction, you'll be more pleased with TOA reflectance image than atmosphere corrected. You see what I mean? It requires a lot of pixel by pixel, condition of the pixel affects the result. So you see some kind of patchiness or discontinuity and stuff like that. TOA are just visually pleasing. Anyway, he mentioned, yesterday that if you're looking for agricultural application, NDVI, almost not much of an effect of atmosphere correction, because majority is happening in blue and green short wavelength channels, right? But if you're doing something, maybe much colorful and vibrant colored image that's desirable, then you have to do it, right? If you look at the spectrum, TOA reflectance is kind of just dull boring from top to bottom, blue to green to red, right? Regardless of the type, surface type. If vegetation, bright sand, they just both are like this. So the spectral difference in the magnitude is very small, but somehow our computer algorithms do something. But if you convert it to surface reflectance, of course there's a clear difference between vegetation and sand, right? So if that's desirable, then you have to do it. You'll do it. But to some degree, what I'm saying is it's not that difficult to achieve that level of correction. But how precise it is, that's a question. Farhan showed a good plot yesterday, right? The ground truth AeroNet AOT versus all the 14 models used based on their own estimation. It's pretty broad range, but still that looks like huge difference in AOT doesn't translate to huge difference in reflectance. Not much, because majority is handled by Rayleigh. Rayleigh is kind of universal for every conditions. So in really high aerosol conditions, it's a problematic, but in that case, your data is not that useful anyway. So overall, I mean, to some degree of just decent degree of atom correction can be always not that difficult.
Okay, I think we have time for one more question. Did you have a question, Ignacio, or you? Very quickly, and then.
It's a great question. I have a question for Minsu. Really want to commend you for the study you've done. I think it's really interesting, and I think one of the questions for us in terms of interoperability is how do we start standardizing some of these analyses you're doing? Like, do you think we could all essentially have kind of the code behind of the analysis you're doing kind of sitting in the open and then contribute like the data, benchmark data sets that we can use to start tracking in detail the ability to make interoperable data?
My just quick thinking is, maybe Greg can tell better, but let's say just take advantage of Sentinel or Landsat. They're doing constant monitoring of radiance conditions and later correction afterward somehow, right? So they always produce good theory reflectance and radiance data. You can just do statistical analysis for a certain selected wide range of brightness and come up with your own, because you don't have onboard monitoring systems and later collection, right? So that's probably a good practical way of improving your radiance product, I think.
Thank you.
All right, thank you too very much. And we're going to take a quick 5-minute break, let everyone stretch their legs. I have 10:03, so 10:08 we'll start the next talk. Thanks.